Welcome back to Algorithms and Uncertainty. We've already introduced competitive analysis for online algorithms, and we've also seen examples of such online algorithms. But those were always designed pretty much in an ad hoc manner, meaning to some extent we were just lucky to find them. Today we'll introduce a much more thorough, much more general technique to design algorithms for online settings, which is also useful in offline settings. We'll see this in a particular problem context, namely the problem of set cover, but it is also useful for other problems, as we'll see later on. The general technique is to write the problem as an integer linear program, then to relax the problem so that you'll have only a linear program, and then you'll try to find a solution to this linear program online. And you do this via LP duality. Maybe or maybe not you've heard of LP duality before. Luckily for us, we do not need a lot of knowledge about LP duality. We do not need the really difficult things. We only need some very basic insights, which we'll all prove today. And then in the next lecture, we'll actually, based on the knowledge that we've derived today, we will then get to design actually an algorithm for this online set cover problem. But first of all, how is this problem defined? So to be precise, we are talking about weighted set cover here. And let's maybe just first talk about the offline problem, which I hope many of you have seen before, but if you haven't, that's no problem. So this is an NP-hard problem. How is it defined? Our input is a set U of elements, which we'll usually call the universe. And then we have S, so this script S, which is a subset of the power set of U, which is a family of n subsets of U, and we'll have a cost for every set in this family. Our goal is now to find a cover, which is a subset of this family of subsets, such that the union of all the sets in our cover is U. Or in other words, every element from our universe gets covered by at least one set in our cover. And we want to minimize the sum of the costs of the sets in our cover. And our assumption is that there is a feasible solution, which means that the union of all sets S in the set script S in this family, this is U. So what does this mean? I've seen, for example, the following explanation, which I find very amusing. We have a set of superpowers, and we now want to find a team of superheroes who cover all of these superpowers. Each superhero that we might hire covers some subset of these superpowers, and so this script S, this is the set of all possible superheroes that we might hire. And now each of them has a cost for us to hire them. Our goal is now to find a team of superheroes, which is this set C, which is only a subset of all possible superheroes that we could hire. And so that all of the powers that our team should have, they actually have. So that the union of all these sets S, so S, that is a superpower of one of these superheroes, or this set of superpowers of one of these superheroes, that they cover everything that we want, all our M superpowers. And at the same time, we want to spend as little money as possible. So the sum of the costs that we'll have to pay to hire them, this has to be minimized. And our assumption is that for each of these powers, there is at least one superhero who we can hire who has this power. Which, in other words, means that the union of all sets that are available to us, that their union will be all of you. But we hope that we can only take a subset rather than the full set to make our solution cheaper. How do we turn this into an online problem? Well, there can be many online problems of interest. We'll turn this into an online problem as follows. This set U of M elements, this is what arrives online. So this is revealed to us one after the other. And whenever such an element of U is revealed to us, only then we get to know which sets in our family actually covers this particular element, and then we immediately have to cover this element, and our decision is final in the sense that once we've added a set to the cover, then it stays in the cover. We cannot remove it anymore. So let's write this down. So in the online version, this universe arrives online, and when an element from the universe arrives, we'll get to know which sets S it is contained in, and we'll have to make sure that E is covered by our cover C by maybe adding one of these sets to our cover. Have we seen such a problem before? Yes, we have. Namely, we've already seen this the ski rental problem. And this is indeed a special case of this set cover problem, of this online set cover problem. How so? Let's see this. Well, in our original formulation of the ski rental problem, we said every day we get to know whether or not it is a skiing day. Let's simplify our life and let's just assume that every day is a skiing day. We just don't know how many days there are. This is just an equivalent formulation. How can we capture this setting? Well, it is actually pretty easy. We now have the following sets to cover our universe. We have the singleton sets, and we have one set that covers the entire universe. The cost of such a singleton set is 1 for every element. And this means nothing but renting the skis on that particular day. And we have the option of buying the skis, which means that we're covering all elements at a time. So we cover the entire universe. We'll have to pay B, and the question is, of course, and you immediately see that the offline problem is trivial in this case, as opposed to the general case, which is NP hard, because we'll only have to see how big is M. Is M bigger or smaller than B? And depending on that, you'll either choose only these singleton sets, or you'll cover the universe altogether. What we want to do next is introduce the relaxation of this problem as a linear program. And to this end, we'll first write down the set cover problem as an integer linear program, and then we'll get rid of the integrality conditions to have a linear program for which one can, in principle, also use fractional values. So how could we write this down as an integer program? We'll have variables xs, which mean that xs should be 1 if the set S is included in our cover and 0 otherwise. And if we were now to write down our problem, we would say we want to minimize the cost of our cover, which means nothing but that we want to minimize the sum of the CS times XS subject to the condition that for every set S, for all sets S which contain a particular element, their sum has to be at least 1 for all elements. So once again, for every element, we ask which sets cover this element, and we just add up all these XS variables, and this sum will have to be at least 1. And also we'll say that XS, of course, should be 0 or 1 for every set. Good. This problem is nothing but the standard set cover problem. And what we'll do now is we'll replace this integrality constraint by the constraint that XS should somehow be between 0 and 1. Then we'll get to a linear program. So what we'll have here is that XS should somewhere be between 0 and 1. And as a matter of fact, this second part here, that XS is at most 1, that's not really crucial. This is why we'll leave this out. Why? Because any value of any XS which is strictly greater than 1 doesn't help anybody at all. If one of these XS's is strictly greater than 1, then we could just reduce it to be equal to 1, and then the respective constraints would still be fulfilled. And this will only improve the solution. So in an optimal solution, and also in any solution that we'll be considering, we will always have this fulfilled implicitly, and this makes it easier for us to state the problem and our approach. So these XS's, they definitely have to be non-negative. But it is okay if they are huge. That's just something that we allow because it doesn't hurt anybody. Good. How does such a problem, why is this now a relaxation? Well, let's see a quick example. Let's see a very quick example why this is a relaxation. So we might, for example, have the following universe of elements. We would have 1, 2, and 3, and then we'll have the sets that cover 1, 2, and 3 as 1 and 2, 1 and 3, and 2 and 3. And the cost of each of these sets is 1. What would be the optimal integral solution? What would be the optimal set cover solution? Well, we'll have to definitely take 2 of these sets. So the optimal integral solution has cost 2. But there is a cheaper fractional solution, namely to set each of these variables to a half. What will happen now? Why is this a feasible solution? Well, for every element, we have 2 sets that cover this element, and their respective values sum up to exactly 1 in this case. So this is also a feasible solution, and what you can see is that the cost of this solution will be 3 times a half, so 3 halves. This is even the best fractional solution, as we'll prove in a second. And it's not really that this example is super crucial, but there we'll see the technique of LP duality. But before we do this, let's also consider what it means to solve such an LP relaxation online. So maybe let's once again write down the LP relaxation. We are to minimize the sum of these CS times XS subject to these XS summing up to at least 1 for all the sets which contain a particular element, and as I was saying, these XX, XS, they should all be non-negative. So what does this now mean in the context of our online problem? In our online problem, as I was saying, will these elements arrive one after the other, and whenever an element arrives, we get to know which sets it is contained in. And this has a particularly nice interpretation also in the context of this LP, namely, you see this is what depends, this constraint is what encodes what elements, what sets an element is contained in. So, what actually will now happen is that these constraints are revealed to us one after the other. And whenever a constraint is revealed to us, then we have to change the solution. And how do we have to change the solution? We have to change the axis so that the newly revealed constraint is fulfilled. And what are we allowed to do? We are allowed to increase the variables. So the fractional version of online set cover is to say that in each step, one constraint is revealed, and we have to increase the XS so as to maintain feasibility. Ideally, of course, we would want to maintain the XS's also so that they are integral, because that would correspond to a solution to our online set cover problem. And there also increasing is exactly what we mean, namely we cannot revert a decision to have taken a set, so every set that has been taken so far has to remain taken. Now we kind of relax this in the the exact same way that we say, okay, we'll have to make sure that these variables never decrease. And as it will turn out, solving this fractional version of the set cover problem will be really helpful, because we can then turn an algorithm that solves this problem also into an algorithm which solves the original problem that we were having. But this is something we'll do later, namely only after we've derived an algorithm for this problem. But let's quickly see this in one more example, what this means, namely, what does this mean in our favorite example of set cover, of online set cover, which is ski rental. So there we have again the objective to minimize something, and let me now rewrite this a bit so that it is easier to read. Namely, I now have variables which are called xbuy and xrent t, and you capture this by exactly the way. So as a set cover problem, you model this exactly the way we saw earlier. So this would correspond to the set which covers the whole universe. This would be the set that covers only element t. And what are now our constraints? We'll have for every day the constraint that xbuy plus xrent t will have to be at least 1 for all t. And also that these are non-negative. So in the set cover problem, things are easier because every element can be covered in only 2 ways, namely by the buy or by the rent. Or, well, now what we are allowing is also to say, okay, I buy half of the skis, and then I have to rent only half of the skis. This is something that we now also allow, and as I was saying, later on we'll also see why and how we can turn this into a solution of our original problem. But as we had for the general fractional version of the online set cover problem, these constraints get revealed to us one after the other, which means every day we get to know whether we are going skiing or not. And then we'll have to increase the variables, or maybe not increase them. So if we've already bought the skis, then of course we don't have to increase the variables because this constraint is already fulfilled. But if this newly arrived constraint is not fulfilled, then we'll have to increase the variables so that we're getting a feasible solution. And the big question is, how do we want to increase the variables so as to ensure that our solution will always be good, that there will be no surprises in the future? We've seen this in a way for the ski rental problem before, but how do we do this in a much more general sense? And the way we will do this is via LP duality, which maybe or maybe not you've seen before. In any case, we'll introduce this in a second. The way we'll approach this fractional online set cover problem is by LP duality. And to introduce LP duality to you, I've once again copied this example, which we had before, for which there was, well, we had the optimal integral solution of cost 2, but we have a cheaper fractional solution of cost only 3/2. Here you could ask, is there a cheaper solution? Could we find something cheaper than this fractional solution? And then you might wave your hands and say, probably not. Probably I have to cover each of these elements by a fraction at least a half, and so on. And probably you'll come up sooner or later with the following proof that there is no cheaper solution than this one. Namely, why is this? Take any feasible solution x. What will happen? What is the objective function value? So if you add up all these three variables that you have in the LP relaxation, well, we'll take a half of the variables which contain 1 plus a half of the variables which contain 2 plus a half of the variables which contain 3. And this way we've rewritten this objective function, and just in a pretty straightforward way, although the meaning is not obvious immediately if you've never seen this. But what will happen now? Well, we know that this is a feasible solution. And what does this mean to be a feasible solution? Well, this will have to be at least 1. This will have to be at least 1. And this will have to be at least 1. Because all these three elements are covered in fractional totally, if we add up the fractions by at least 1. So we'll have that here, what we have here on the right hand side, this is always at least 1 due to the constraints. And so we'll get that this is at least a half plus a half plus a half. So 3 halves. Which means that for every feasible solution, the objective function value will be at least 3 halves. So this is just one kind of ad hoc proof that one cannot do better than 3 halves in this case. But the amazing thing about LP duality is that you can kind of always do these kinds of proofs. You always find a way to rewrite your objective function so that then you can apply the constraints to then get an upper bound, in this case, of the objective function value, in the case of a minimization problem. What will this look like for set cover? For a set cover, we have the following linear program, which we call the dual of the set cover LP relaxation. We'll have to maximize sum of ye. Ye, those are new variables which we'll call dual variables. and we'll have the following constraints. We'll have the constraint in the dual that for every element, the sum of the YE that are contained in a set S sums up to at most CS. And that all these YE are non-negative. Let's see this again in the context of our example. What does this mean? What is a dual solution? A dual solution is nothing but these YE, where we now have for every element we have a variable, whereas before we had for every element we had a constraint. And these are now these multipliers here, which we were using in this example before to rewrite the objective function value. And the fact that we use what we actually used here was that this here is actually this only needs to be a lower bound in this case for this argument to go through. And this is why we have an inequality here. But the way you can think about the dual of an LP is just like this. The dual gives you a structured approach to show that no feasible solution will be better than a certain value. And this is exactly called weak duality. Let's write this down. If we call X and Y feasible solutions, to the primal and dual program, what's the primal program? This is just in the context of set cover, the LP relaxation that we were starting from. So, because for every linear program, there is a dual, and the thing that we're starting from, this is what we then call the primal program. And if we have two feasible solutions, one for the set cover primal, one for the set cover dual, then we'll have the following, that the cost of the primal solution will be at least the cost of the objective function value of the dual solution. So this is the objective function in the dual solution. This is the objective function value of our primal solution. This is the objective function value of our dual solution. And what we'll see is that the best or any feasible solution for the primal LP is no better than any solution to the dual LP. So if you want to think about this pictorially, you have some possible values for the primal solutions. You have objective function values. You have some other values, possible values for the dual solution, but those never intersect. So maybe let me also draw this. Would have dual solutions maybe here, and primal solutions may have objective functions values which are here. So we are always, in both cases we are comparing the objective function values, and the duals will be somewhere here and the primals will be somewhere here. Good, let's prove this. Weak duality. This is so insanely easy. I'm almost embarrassed to prove this here, but let's still do this. What do we have? Let's start here from the right hand side. How big is the sum of the YE? Well, let's rewrite this as 1 times YE. Okay, good. Now how big is 1? Because we can now use the primal constraint for element E, we'll have that the sum of the x's for the s's which contain E, this is at least 1. So this here, this is coming from the primal constraint. Good. Now let's reorder things. We might also instead add up over all possible sets, take the value xs, and then add up all elements E in that set and take the sum over all the respective y. This is just reordering this sum here. Now what do we know about this quantity here? I hope you recall what the dual of the LP looked like. It says then this should be no more than CS. So we can also write this as an upper bound. We can say that this is no more than the sum of the XS times CS, where this here, this is now coming from the dual constraint. And in combination, you see, okay, the primal objective function value is at least the dual objective function value. Let's come back to our example of ski rental. What's the dual of the ski rental LP? Maybe let's quickly go back to the primal ski rental LP. Here it is. So we have for these are the elements that we have. Those are the days and the possible ways to cover them. Those are the options of either buying or renting. And if you now do this here, you'll see, okay, we'll have to now again maximize some of the YT And what are our constraints? Our constraints are that, well, on the one hand we have this dual constraint for the by option, which means that the yt shouldn't sum up to more than b. And on the other hand, these yt should be no more than 1 for all t. And all of them should be non-negative. So what does this mean? Well, we'll have two kinds of constraints, and the way you can think about this yt is how much are you spending on day t? And the two constraints mean, well, on the one hand, you shouldn't be spending more than b for all days together, and on the other hand, you shouldn't spend more than 1 for every single day. And your goal is, of course, to spend as little money as possible. If you were doing something which is bigger than this, then you are apparently suboptimal in your choices. What might be a little confusing here is that why is there this maximization objective? Who would want to maximize this? This is at least a little confusing to me from time to time, but the point you should think about this is whatever we are now constructing, or the solution that we are now deriving, if we are able to state an LP solution for this, which has about the same cost, then via weak duality, we can show that this LP solution, or that the solution that we are coming up with, is approximately optimal. And this is the first thing that we'll do now. Namely, we'll come back to the ski rental algorithm and once again analyze this, but in the context of LP duality. I now want to come back to the ski rental problem and the very basic algorithm that we had for this. Namely, and every day you ask yourself, how much have I spent on renting skis? And if I have already spent enough on renting skis, then I buy skis. Otherwise, I still keep renting them. We'll now redefine this algorithm a tiny bit so that it fits into this fractional context here. And what we'll do is we'll say, okay, actually every day you just don't buy your skis, you don't decide to rent or buy your skis, but when you're renting your skis, you also buy a tiny fraction of your skis. This is something that we are allowed now. And we'll do this up to a point at which we'll have bought all of the skis, and then we don't have to rent them anymore. This is clearly suboptimal for the fractional case, and as a matter of fact, we'll soon see how one can do better in this context. But let's first write it down like this. So if we have not fully bought the skis yet, what will we do? We will increase the buy variable by 1 over b and the rent variable for the current day by 1. And what else will we do? We will set yt equal to 1, which means that we are keeping track of how much are we spending. And this we will later use as a dual solution. And If we've already bought the skis, then we don't do anything and we set yt to 0. And to turn this not only into a fractional solution but also into an integral solution, I also say that if now these buy variables are 1, then I want to buy the skis otherwise we rent them. So this algorithm is actually even a little more than what we need for the fractional problem, because for the fractional problem it would be only these lines would be enough. We would only have to make sure that we're getting at least 1 from the skis. Here now, this part is even turning this into an integral algorithm. And what you will realize is that this is more or less the algorithm that we discussed. Namely, the first b-1 steps, you will always do this here. You will always increase x by 1 over b and x rent t by 1. But there, always this x by will be smaller than 1, which means we are not yet buying the skis. But then, on day B, we suddenly reach here 1 by adding 1 over b once more, and then we are buying the skis. And what we'll show is that this is actually a two-competitive algorithm, which is actually no surprise, because this is what we also showed when we were talking about the ski rental problem, that this is actually a two-competitive algorithm. And what we'll do now is we will now show this via LP duality, using this weak LP duality that we've already shown before. So what will the cost be that this algorithm will incur? It's actually even a little less than what I'm writing down here for tiny technical reasons, but it is surely less than b times x by plus the sum of the x rent t. Why is it even a little less than this? Well, there is this weird day b at which we're still increasing the rent variable and also increasing the buy variable. And so this is not exactly matching what the cost that we are incurring then, because we don't buy and rent the skis on day B, we only buy them, but that's just a minor detail here. Good, so we now claim the following. We let x star be any feasible possibly fractional solution to the ski rental LP, and we let x be the one computed by the algorithm. Then we have that b times x by plus the sum of the x rand t is at most 2 times b times x by star plus the sum of the x rand t star. What does this mean? This means now the following. This is an upper bound on the cost that our algorithm will incur. And this here, this is the cost of this optimal or any feasible fractional solution. So in particular, you could, for example, take the optimal solution. And this now means we are only off by a factor 2. Our cost is at most a factor 2 bigger than the optimal cost, which means nothing but that our algorithm is too competitive. Let's prove this. If we let xt be the state of x after the tth step, and we also call x0, 0, then what do we have? We have that b times x by t minus x by t minus 1 plus x rand t is at most 2 times yt. Why is this? Let's look again at the algorithm. In this algorithm, we say that by how much does x by increase? It increases by 1 over b, and x rand t increases by 1. This happens only if we set yt to be 1, and otherwise we set yt to be 0. So this is exactly what we're using here. We have x by t. This is the increase of x by t. This increases by 1 over b if yt is 1, otherwise the increase is 0. So multiplied by b, this thing here will be no more than yt. And the same for this here. For this here, we also have that this is at most yt. Good, what do we now get? If we now take the sum over all t, then we get that b times x by plus the sum of these x rand t, this will be no more than 2 times the sum of the yt. Okay, so we've now shown that this here in what we're trying to bound with our theorem is no more than 2 times the sum of the yt. What else do we have? We now know that this y is actually a feasible dual solution. Why that? Maybe let's quickly go back to the dual of the ski rental LP. What do we have to have? These yt should add up to no more than b, and each of them should be no more than 1. So if we go back to our algorithm, then what will we see? We will see that here these yt, only the first b of them will be 1, afterwards they will be 0. Which means they sum up to 1, and also each and every one of them is no bigger than 1. So this means that y is a feasible solution, a feasible dual solution, because no entry is bigger than 1, and all entries sum up to at most b. And if we now apply weak duality, this tells us that for this any feasible solution to the primal, this objective function value will be at least what we have for the objective function value that we have for the dual solution. And so this means that our algorithm is too competitive. Why that? Because this here that we have here on the right hand side, this is what is at least as good as the optimal offline solution. So our objective function value, or our cost, is no more than 2 times the optimal offline solution. And this precise way of thinking about algorithms, or more precisely to upper bound the cost that our algorithm incurs by keeping track of how much are we spending every day, this precise approach we will now be using to understand and design and analyze algorithms for the online set cover problem. So where are we now? Where are we so far? We've seen that LP duality helps us bounding the competitive ratio of algorithms. Namely, its main feature is that it gives us a bound on how good the optimal offline solution can be. And now we will sum up everything that we've seen today in actually just one technical lemma, which then in the next lecture will be useful for us to then derive and analyze an algorithm for the online set cover problem, or more precisely the fractional version of the online set cover problem, which we will then later on also turn into an integral algorithm. To simplify our notation, we assume that in this online set cover, the tth element arrives in the tth step. So recall that the universe of elements was called 1 through m, and I said, okay, in every step one of the elements is revealed, and there's nothing preventing us from saying, okay, in the tth step, the tth of these elements is revealed. And now what we'll do is the algorithm maintains a feasible primal solution xt, which means that this, of course, fractionally covers the elements 1 through t, and it also constructs a dual solution This dual solution is possibly infeasible. We'll call this y, and yt, this is how we think of the cost that we incur in the tth step. And to analyze such an algorithm, we will use the following lemma. It says that if in every step t we have that pt minus 1 is at most beta times yt, where pt is the cost that our algorithm incurred up to step t, and also we want to have that 1 over gamma times y is dual feasible. And then the algorithm is beta times gamma competitive. Let's once again understand what we're saying here. So we are now constructing, or more precisely our algorithm, is maintaining this feasible primal solution, which we call xt. This is what covers everything that was revealed to the algorithm up to time t. And then a new element gets uncovered in time t. So this is xt minus 1, this is what we had up to before time t. Then in time t, another element gets revealed to us, meaning a constraint in the primal LP. Then we'll have to increase the x variables. And not only this, we will also write down somewhere how much we are paying. This is what we write down as yt. This is the cost that we are incurring now. And what we'll now want to have is that all we leave us some slack that this primal increase is at most beta times yt. So by yt we mean how expensive was it for us to cover element yt, no, to cover the teeth element. And what you see here, this is actually the cost increase that we have, because this is by how much do these variables increase, or by how much does the objective function increase. And then we want to, on the one hand, have that this increase is bounded by beta times yt, but on the other hand, this is the second part here, we want that this is close enough to a feasible solution. We want that this is a 1 over gamma times this is a feasible solution. If, for example, both of these were 1, then we would have a dual solution, a feasible dual solution, which also keeps exactly track of the money that we are spending, of the cost increases that we have, and then we would be 1 competitive. Well, this is too much to hope for, and therefore we have these two factors beta and gamma involved here, which now tell us that, okay, we don't have to keep exactly track of how much we're spending, and this doesn't have to be exactly dual feasible. It only has to be a scaled down version of it has to be dual feasible, and then we have a competitive ratio of beta times gamma. Good. Let's see that this is actually an easy consequence of the of weak LP duality, and just a way of rewriting LP duality in this context here. So what do we have to show? We will show that this PT, the cost that we've spent up to including step T, is no more than beta times gamma times the cost of any feasible x star So at all points in time, the costs that the cost that we've incurred is no more than this factor beta times gamma times the cost of any solution, so in particular the offline optimum. Good. Why is this true? Well, on the one hand, we have that we can write PT as a telescoping sum of PT prime minus PT prime minus 1. And then we know, okay, each of these terms we can bound by beta times yt prime. So we'll have that this is no more than beta times the sum of the yt prime. What else do we know? We know that by B and weak duality, we'll have that the sum of these of 1 over gamma times the yt prime, this will be no more than what we're getting the cost of this feasible solution x star. And if we now combine this, then we indeed get that pt is no more than beta times gamma times the cost of this cs times xs star. So the math involved here is really nothing mysterious. It is actually extremely straightforward, although I think this is something one might want to digest again and again. At least it took quite some time for me to understand what is really happening here. But what was it on a very fundamental technical level that we did? We just had that we write pt, this is the cost that our algorithm incurs overall, and we can upper bound this in terms of these yt, this dual solution that we're constructing, which is not only in a scaled down version, it is feasible. And then we also have that this yt is again upper bounded, its cost is upper bounded by the cost of the offline, optimal offline solution. And this then is our lemma, which we will again use in the next lecture to then derive not only an algorithm for fractional set cover, fractional online set cover, but also for fractional ski rental. So what will we have to do? We will have to make sure that our primal increases are no more than what we beta times what we are counting as the increase, and also that the increases that we're counting divided by gamma are dual feasible. And as a matter of fact, we've already used this lemma. We've not used it explicitly, but we analyzed this algorithm for ski rental. And this algorithm for ski rental that we analyzed, as a matter of fact, for that we showed that this factor beta was 2, this factor of gamma was 1, because this was a feasible dual solution that we constructed, but in every step we had a cost increase of up to 2 times what we put into our account with this yt. And then we got to the point that we had a 2 competitive algorithm. And as I was saying, what we'll do next time is we will try to use this lemma, and not only try, but we'll also succeed using this lemma for fractional ski rental, and then not fractional ski rental and also fractional set cover. And then what we'll do is we'll just try to find something that really makes these inequalities tight. Or we'll try to keep this factor beta as small as possible, and then this will mean something for the factor gamma that we are incurring here. Good, this is it for today. Please let me know if you have any questions, and let's hope we can see each other in the next lecture. Stay safe in the meantime. Bye.